Okay, so this is gonna talk here. It's the FPGA here. We can see it here. This is the board. If you come over here, you can see it in real as well. It's an Altera FPGA in the middle. When there's four CAN channels, and we are using 2 here in the demonstration. And there's a PCI Express bus up to the PC computer. We make mostly in Kvaser CAN interfaces, so this design is very much optimized for that type of application. It's in a small Cyclone 4 FPGA with 15K logic. It's roughly 2.5K for each CAN controller, and 5K is for DMA and the PCI Express interface. And it's a combination of CAN, CAN-FD, and CAN-EF. I'm going to talk more about CAN-EF. CAN-FD, I think you already know. And there is, as you can see, a galvanic isolation as well. I hope I don't going to talk very much about CAN-FD. I hope everybody have got that information. But here you can see the difference from a standard CAN with 1 byte and a CAN-FD. So it really shrinks the length of the message, because not just because of the data, but it's because the CRC as well is shortened. In this case, it's a 5 double, so it's 1 megabit and above and 5 megabit, 8 megabit in the lower case there. So let's see in the real life how it looks like. So this is a standard CAN frame running. So if we now switch to the EF, let's see. I have to do one more thing. I'm going to start our we do. I was planning here to, why doesn't it work? Okay. I show that later. So we have 2 solutions here. So if you switch, now this is a tool we have to test things here, where we can select different protocols, like CAN, CAN-FD, and CAN-EF. So if you look at, if you now start the CAN-FD here, so there you see, here we can then select, switch in CAN-FD. In this case, if we can select a number of bytes. So if you have 8 bytes of data, you see here the CAN-FD is very short compared to the standard CAN 8 bytes of data. So so even if 8 bytes of data is very important to switch to CAN-FD, because you shrink it a lot, because you shrink also the CRC. And what we have done at the CAN-EF here what happened here is that in CAN-EF we put the high-speed bits into a standard CAN frame. So this is backward compatible. So if you use a standard CAN controller, it will sample the bits here, and each sample point will be correctly according to the CAN protocol. So he will assume this data together with the CRC is a correct CAN frame, and just acknowledge it as a standard CAN frame. But the CAN-EF controller will, of course, detect them as a CAN-EF frame and find out all the other bytes. So you can hear, if you can switch up to the to 64 byte, then we see it's quite long with the CAN-EF. But if you turn the CAN-FD, it becomes shorter, because the CAN-EF cannot utilize the whole part. We have to protect the sampling point. So we cannot put the data in the sampling point. That has to be protected by the CAN protocol. So the CAN controller will read the correct sampling point. So roughly, you can see the difference. This is both are 64 byte, and you can see the difference with the CAN-EF and CAN-FD. So it's roughly 40% shorter because CAN-FD can utilize the whole amount of time in the frame for that purpose. And these tools, we also here can check when we're running here. In the logic, we have put in a dynamic clock here. So we can add a clock arrow to one controller, and then we can see at what clock arrow we get error frames. And that's funny when you do this, because how the clock variation you can have in a CAN system is not only static. So if you have a system running for one data, it's very important here now to turn on arbitraging data and CAN ID to really squeeze the system. So here we can see by the offset. Let's see. System to see how it works, and this is a tool we're using to verify our CAN implementation. So we can change both the clock between different modules and also automatically adjust the delay time. So you can check that our solution is robust against the different delays. So we can synthesize the different cabling length in the tool. Similar to like Unicor is doing, where they have their testing simulation, where we can adjust different things to force different scenarios into the CAN communication. So I come back to this later. So that looks into the presentation and the paper, how our solution looks like. First of all, you can see that CAN-FD is not that demanding, because in CAN, you can see in this example, if you have a CAN bus at 1 megabit, roughly you will need 8 time quanta in each bit to have a dynamic in both for the phase segments and the propagation delays. But if you look at here at CAN-FD with 3 megabit, you only need 9 time quanta in each 9 megahertz sampling point time, because you can live with only 3 time quanta in CAN-FD bits. So the demands for the logic in CAN-FD is not as high as in CAN-FD when it comes to the physical layer. So to me, my point of view, to use CAN-FD is the complexity to use CAN-FD is the same as increasing the bit rate on an ordinary CAN controller. So if you have a system running in 250 kilobit and you want to switch to C750, you will have the same problem doing that as using CAN-FD at 750K. And one important thing with CAN-FD as a higher bit rate is that you can get more data into the time. So even if in this case we have a switch here from 8 times, where we have 64 byte in the lower diagram, and that's even shorter in time compared to 8 byte in CAN. So, and that means that you have the 8 times more data, but the real-time performance will be the same in both those systems using this kind of CAN-FD installation. And most of it is because the CRC is shorter. Our implementation is very similar to Unicor solution. We make interfaces, and that means that all information we get from the CAN bus has to go up to the application. When you make an ECU, normally you're only interested in a few percent or maybe 10% of the communication, but in a PC computer like analyzing tool, diagnostic tool, then you need 100% of the information. So we don't have very much use for filtration, things like that. So everything we get here jumps into the RX FIFO, The same as the tagging information in the core, we just put that into FIFO. We have only one stream and just put it up to the PC application, and they have to take care of the information. And normally there's only 1 or 2 messages in the FIFO. It's because it's DMA, so it goes to the PCI Express immediately up to the application. This is the basic core of it. It's the first part you see there is the CAN handler. It goes to the CRC generation 15, and then you see one part. That's what has added up here into the installation to handle CAN FD. So it's only 2 parts that's included for CAN FD, and it's the CRC generation and the secondary sampling point. You can see it's marked with CAN FD. And then it goes down to comparing for bit compare, the sampling of the bits, a secondary sampling point, some timing, and then you go to the handling of the time quanta on the bus side. And the EF part is just something parallel here, some running in parallel with the CAN communication, because CAN EF is just the additional bits into the CAN frame. So the complexity really comes to the CRC calculation and the time quanta bit handling, because now we have to have 3 CRC calculations, and there's a lot of the decisions that has to be done in real time, because we don't know which CRC we are going to use until we get the data, because the CRC selection is depending on the data length. And this is simplified. It's not the error handling is not included in these pictures. It's just pure handling when everything is working. So it's a lot of control system around this as well. So this is showing the difference, as you can see here, depending on the DLC. In standard CAN, it's quite simple. It's up to 0 to 8. It is 0 to 8. And more than that, you only have to handle, it's only 8 bytes of data you have to send out on the bus and receive. But when it comes to CAN FD, we have to check, because if it says 9, it will be 12 bytes, and so on and so forth. And depending on the data length, we have to select different CRCs. So this is the basic. We still have to handle 1129 byte DD. But when it comes, we also have to check our DLC in every frame to decide which kind of CRC we're going to use and what type of how handling the remote request, because we still have to handle remote request in the standard CAN. And we have to know where to switch to the higher bit rate and how we use the secondary sample point and the different use of CRC and stuffing. Because CSC has a different stuffing algorithm here. So when we have the standard path, I have to do it. In standard path, the bit goes here and makes the CRC 15, and then we makes the stuffing after we have done the CRC calculation in CAN. But when we use the CAN FD format, we have to do the stuffing before we put it into the CRC calculation. And to solve the ending of it, when we receive the CRC calculation, there's a different stuffing algorithm to handle the CRC part of it. And the secondary sampling point is to be backward compatible with CAN, because normally when you send CAN, you check every bit that you're sending that is correctly showing up on the bus line. But due to the high speed of the bits, they are so short, so the delay in the transceiver is big enough to cover up the bits, so we cannot check them without handling that. So what happened here is that when we have the FD format bit makes dominant, we can measure how long time is from we transmit it until we receive it back on the receiver side. Oh, thank you. Okay. So here you can see we calculate and measure the time from this edge until we get it back from the bus through the transceivers. And by putting in that as a compensation here, we have to save the cent bit here and compare them with the right location in time with the bits coming back from the transceiver. So now we have seen a little bit of the CAN EF format, and hopefully I can show you some more here. And the CAN EF, it's backward and forward compatible, so you can run the CAN EF frames in a CAN FD world, because the CAN FD controller, if they don't support CAN EF, they will consider CAN EF just a standard CAN frame and just ignore the edges in the CAN EF added into the CAN frame. So this is how it looked like if you look at it in the detail. So this is the beginning of a nominal classic CAN bit. And in the beginning here, we have the propagation segment. And the propagation segment is there only to handle the arbitration. So after the arbitration, every module will be in sync. So that means that we can add in bits here, but we have to stop the number of bits here, because here we have the sampling point where the standard CAN will make the sampling. And now we have to stop our bits, so we are sure that all CAN controller will have a correct sampling here. And then the next bit will come here, and we send more high-speed bits. Now there's a lot of recessive bits here, and that's a dominant high-speed bits, and then we sample the recessive. And now here we will get an edge again, and this edge here will resynchronize them, so everybody will adjust the sync jump width here, using the standard sync jump width protocol to adjust the sampling point, so we all the time get the sampling point in where we expect it to be. So we are protecting our CAN EF bits from moving into and incorrectly sampled by the CAN controllers. So the reason to use CAN EF is that CAN EF will make it as a slowly migration. Like in CAN Open, we have 10,000 different modules and in different systems. And if we use CAN EF, then we can add 2 CAN Open modules supporting CAN EF that can communicate at a higher bit rate in between each other, and all the other CAN Open module on the market can be used in the system with a classic CAN approach. So this is a short way to increase bandwidth in those modules that need increased bandwidth in an ordinary CAN Open CAN system. So, and also we have utilized the same type of CRC or similar CRC calculation as in CAN FD to protect the data better than that it was before in CAN. So yes, we will. So we see CAN EF as a tool to get it easier transfer into the CAN FD. As we've seen before, we can increase the information flow in the CAN communication with the CAN EF, but we cannot never compete with CAN FD, because CAN FD is protected. So it means that they can more efficiently utilize the time. That's about all. I think I could show more here, but I think it's better if you come up to our booth, and then we can show you in detail and explain it on the desk how it's working if you have more questions.